Hi friends, you're welcome to today's lesson. Today we're going to be solving some of the take-homes we are given to test ourselves on what we discussed in our previous lesson on calculation on isotopes. In our previous lesson, we did quite a very good job on calculation on isotopes, and we're given a couple of questions to test how much we learned from that very given lesson. So this was the very first question we were given. Boron exists as an isotope mixture containing 80% of boron 9, 15% of boron 10, and 5% of boron 11. Calculate the relative atomic mass of boron. We are asked to calculate the relative atomic mass or the average relative atomic mass unit of boron. Now, don't forget the formula. There's a formula given to us, to use each time we are asked to get the relative atomic mass unit of any given element, provided we are given the percentage or the isotopic abundance of the various isotope samples of that very given element. And don't forget, what's the formula? The formula is simply the summation of the partial atomic mass unit of each isotope given to us. Now, how do we get the partial atomic mass unit? Don't forget the formula also. To get the partial atomic mass unit, it is simply the isotope abundance over 100 times the given atomic mass of each isotope. That's what you're going to do. So it's very simple. So what I'm going to do first, the first isotope given to us is boron 9, the second is boron 10, and the last is boron 11. So we're going to be solving each of them. Going to be getting 80% of this, 15% of this, and 5% of this. So that's going to be 80 over 100 times the first atomic mass unit of the first isotope. This is over 1. Then summation, we're going to be adding them all up. So that's 15 over 100 times the next isotope, 10 over 1. Then the last 5 over 100 times 11 over 1. So we're going to be punching in these figures into our calculator to see what we're going to get. So by the time we get each of the, we're going to get a partial atomic mass unit for each of the isotopes. So the first we have here is 80 over 100 times 9 over 1. So let's punch that in. 80 times 9 divided by 100. So we have 7.2. So the partial atomic mass unit for the first isotope is 7.2. So the next 15 over 100 times 10 over 1, we can easily do this. 10 and 1, 10 and 10. That's 1.5. And then the very last one, 5 for 100 times 11 over 1. When you times this, 5 times 11 is 55. 55 divided by 100 will give us, you know what that's going to give to us? That will give us 0.55. 0.55. So when we do the mathematics, when we add them up, 7.2, 1.5, 0.55. Let's sum them up. What do we have? That's 5, 7, 12, 8, 9. So 9.25. So what we have here is 9.25 atomic mass unit. As simple as that. That's how to get the relative atomic mass of the very first question. Question 2. An element Y exists in 3 isotopic forms in the ratio 2, 3 to 4. If the isotopes have the atomic masses as 29, 30, and 31 respectively, solve for the relative atomic mass of element Y. This question was the second question we were given, as a take-home to test ourselves with in our previous lesson on isotopes calculation. So it's very simple. Now we've been given the isotopic, the masses of each isotope. For this very given element Y. So what we're going to do first is we're going to state them out. We're going to state out the different samples. So the first is there's the first sample. We have a 29 atomic mass unit. Next we have a 30, and the next we have a 31. So we have all this already. And now look at this. Look at the first line of statement. An element Y exists in 3 isotopic forms in the ratio 2, 3 to 4. Now this very ratio given to us is their isotopic abundance or the percentage abundance. Now each of us to be given their existence in form of percentage. We're given their existence in form of ratio. So it's very, very simple to sort this. So what we have, 2 ratio 3 ratio 4. You can easily say 2 plus 3, 5, 5 plus 4, 9. So 2 over 9 times 100 over 1. So we end up having 200 over 9. That's about 22.222 something percent. So it's the same thing. Either we are going to be given the isotope abundance in form of percent, or we're going to be given in form of ratio. They're all the same. So first, let's get the total the total ratio, which is same thing as 100%. 2 plus 3 is 5. 5 plus 4 is 9. That's what we have. So now let's get the partial atomic mass unit for each of the isotope. So for the first one, which is the one with atomic mass unit of 29, it's going to be 2 over 9 times 29 over 1, then plus. Then the second one is going to be 3 over 9 times, what do we have there? 3 over 9 times 30 over 1. So the last one is going to be 4 over 9 times 31 over 1. As simple as that. So we're going to get each of the partial atomic mass unit for each of those isotopes. So by the time we're done, we add up all of them. Then we end up getting our relative atomic mass as easy as that. Very simple. So let's quickly punch the figures into our calculator. So 2 times 29 divided by 9. What do we have? We have 6.44444 in this recurring decimal. That's 6.4. Then plus the next thing, 3 times 30 divided by 9. What do you have there? We have 10. That's what we have. That's just a whole number. Perfect result. So the very last one is 4 times 31 divided by 9. 4 times 31 divided by 9. What do we have? 13.777. And, as a recurring decimal, as I can say, 13.8 approximately. Let me say that. So what do we have? The next thing, we're going to sum them all up. 6.4 plus 10. That will give us 16.4. 16.4 plus 13.8. That will give us, that is 30.2. That will give us 30.2. So this is our atomic mass unit. As simple as that. Very easy and direct. Okay, guys, this was the last question we were given as a take home in our previous lesson. An element B has two isotopes, B6 and B7. If the relative atomic mass of B is 6.1, find the isotope abundance of each of the isotopes. Now, this is very simple and direct. Now, we've been given the atomic mass unit for each of the isotopes, and also we're given, the relative atomic mass, the average relative atomic mass of the given element B that we're talking about, to be 6.1. Now, we're asked to get the isotope abundance, or we're asked to get the proportion, the percentage proportion of each of those isotopes in nature. Now, it's very simple. Don't forget, we have just two major isotopes. Now, for the fact that we have two major isotopes, it's very easy for us to solve this very question either ways, either ways we prefer. So the very first isotope is this, 6. The second isotope is 7. Now, we are not given the percentage abundance, but we can assume this to be, any of the unknown. We can use an unknown to represent the percentage. You can say let this be X percent. Now, for the fact that we're just given two isotopes, if this is X percent, the other one would be 100 minus X percent. More or less like saying if this is 30% and they are just two, the other one will be 70%. So what do we do next? The next thing we do is we're going to get the partial atomic mass for each of those very given isotopes. So that's going to be S over 100 times 6 over 1 plus 100 minus X over 100 times 7 over 1. So by the time we sum up all of them, we end up with 6.1. So what do we do next? The next thing we do is 6x over 100. Just need your mathematics skills to be up to average for you to understand this. Plus 7 multiplies this, 100 minus x over 100 equals to 6.1 over 1. So what do we do next? The next thing we do is this. We're going to get the LCM. LCM of 100, 100, and 1. We give us 100. 100 divided 100 is 1. 1 times this is 6x. 100 and 100 is 1. 1 times this, we give it 7 times 100 minus x. 1 divides 100 is 100. 100 times 6.1 will give us 610. So the base goes out, the LCM goes out, so we are left with the 1 on top. So that's 6x plus 700 minus x equals to 610. We're very close to getting the value of x. So that's 6x plus 7 times this is 700. 7 times x minus 7x equal to 610. So 6x minus 7x, then 610 minus 700, just here. So what do you have? 6x minus x is x minus x. 610 minus 700 is minus 90. So x takes out x is minus 6 and minus, x is 10. So if the x here is 10, what does it mean? It means the other one here is 100 minus 10, which is 90%. So this exists 90% in nature, while this exists just 10% in nature, as simple as ABC. Now there's another way we could use another approach. We could approach it another way, which is the simultaneous equation, but time won't permit us to do that. If you want to see how we could use that method, you could just check the previous lesson, and that will do it. So at this very point in time, we're drawing the curtain on today's lesson. If you found this lesson useful, please subscribe to the very channel and share this lesson with others. See you in the next lesson. Thanks.